Welcome to the next video in the Measure Theoretic Probability series. This is video 6 on some canonical examples of measures. So you'll see what I mean by that in a bit. We're going to discuss 4 very important examples of measures that we're going to kind of use pretty much to make sense of each thing that we encounter as we go through measure and integration. So they'll be sort of like orienting examples. These are, of course, not all of the examples of all possible measures. They're not even all of the examples of interesting measures that we'll want to discuss. But they are simple enough examples that we can already start introducing them and make some amount of sense of them, even before I have formally told you what a measure is or anything like that. So the first one is length measure, and we've talked a lot about that by now, so I'm not going to say much more than that, other than that the basic idea of length measure is that we're trying to capture the notion of the lengths of intervals, but also sort of use that to extend to helping us talk about measures of other subsets of real numbers that are not necessarily intervals. The next example is going to be counting measure. And so this is an attempt to measure any subset of any set at all, right? So it doesn't have to be real numbers, could be anything. Here in the little visualization that I'm depicting, I'm talking about the set of the numbers 3, 7. It's just an example, could be a set of anything. But what this measure does is it tries to measure that set of 3, 7 as, right, like assigns to it its cardinality, right? So since it has 2 elements, then the measure of this subset is 2. So clearly the measure of the empty set would be 0, and so on. The next example is the probability of some event, right? So if you have some probabilistic sample space, if you have some background in statistics, you'll be familiar with some of this. Then it turns out, once we say what a measure is, then probabilities of events over a sample space will count as an example measure. And clearly that's going to be very relevant for what we do in the second half of the series. And the fourth example is the Dirac measure of a point in space. So here I'm depicting it as just this point in what looks like a 2-dimensional space. So the details won't be important. We can kind of deal with a whole bunch of different details once we formalize this a little more. But, you can have some set that contains the point, and you can have some set that doesn't contain the point. Now, if a set contains the point, then the Dirac measure will assign that set a measure m, some fixed constant m. And this is supposed to, right, this, I think, originally came up in the context of some kind of physics something. And it's supposed to capture the idea of a point mass, a single point that has some positive mass. And so all the other points in space, just to get started, right, like we can talk about, some example where there are a whole bunch of point masses, but at least for now, we'll think about where there's just a single point that has some mass, every other point has no mass. And in that example, so if you take any set that contains the point, all the other points contribute nothing, but the one point, this point x, the privileged point that has a point mass m, will assign that whole set the mass m. If a set does not contain x, then it just has 0 mass. And so that's a measure, right? That's an example of a measure. And we call that Dirac measure. Before moving on, notice that only length measure is an entirely specific measure. We know exactly what we want to be measuring, which is sets or at least intervals of real numbers. When it comes to counting, we could count subsets of any set. So, it's not like there's just one count measure. You could take your universe to be anything and have a count measure for that universe. You could write probability measures are not specified. because you could have any sample space you want and take probabilities over that sample space. So there's lots of options, right? These are not specific examples. These are kind of just categories of examples. And same thing with a Dirac measure. Your point X could be anything. The mass that it has could be anything. So these other examples are not completely specific examples. So I want to just establish some vocabulary about these things. So I've already used some of the vocabulary. And the first thing that I want to just be explicit about is the universe, right? The universe is just any set. And, in principle, for a general measure, we will allow omega, the universe, to be absolutely anything. Now, in the example of length measure, it's completely specific. It is the set of real numbers. And when it's count measure, probability measure, or Dirac measure, technically we can allow any omega, the universe, to be anything at all. We do use slightly different vocabulary in the setting of probability measures, and I've already said this. When the measure is a probability measure, we usually say sample space instead of universe. Now, for a general measure, we call the elements of omega points. It's a metaphorical reference to geometry, even if we're not dealing with an actually geometric example. Like, for instance, the count measure, where those numbers may not be intrinsically geometric. And again, right, special vocabulary for probability spaces. For probability spaces, instead of calling them points, we may call them atomic events or outcomes. I think there's some other vocabulary that some probability theorists also use. But okay, so that's the universe. Now let's move on to the distinguished collection of measurable subsets, right? So the thing in every one of these examples, we're always trying to measure subsets of omega. So for instance, in the length measure example, an interval of real numbers is a subset of the set of all real numbers, and we're trying to measure that. Or if it's the count measure, we take a subset of the universe, a subset of omega, and count it up. But in every example, we're trying to measure certain subsets of omega. When it comes to count measure, when it comes to Dirac measure, we really can just measure every subset. So there really isn't much sense in distinguishing the measurable subsets. But we already know that when it comes to length measure, that's exactly the project that we outlined in the previous videos on the history of measure and integration, is that we must have some sort of disciplined way of distinguishing which sets are measurable and which ones are not. And so when we bundle together all of the sets that we would like to be measurable, we'll have some vocabulary for that. We'll call it the measurable subsets or just the measurables. The collection of all of them is the collection of measurable subsets. I will often denote that with a calligraphic S. When it comes to length measure, I will use the distinguished calligraphic L for the length measurable subsets. When it comes to probability measures, we won't call them measurable subsets. Instead, we'll call them events, right? So the thing that a probability measure measures is still a subset of the sample space, but we call such a thing an event. Now, so said, it makes it sound like we'll just allow, right? If you take any subset of the power set of omega, we'll allow that to be counted as some collection of measurable subsets. That's not true, but we don't yet have the definitions that we need to say exactly what the restrictions on this will be. So more on that later. Moving on, we also have a measure function. This will be a function from the collection of measurables to the extended real numbers. And we have special notation for each of the examples that I've named here. So if it's length measure, then we'll use an M. When it's count measure, we'll use C. When it's a probability measure, we'll use P. When it's Dirac measure, we'll use delta sub x, where x is the point in question that has some mass m. For a general measure, if it's not one of the sort of like distinguished named examples, then a generic measure will be written as mu. Now, just as I said, that we won't let just any collection of subsets of the omega be a collection of measurables. We'll have certain requirements on it that it must satisfy in order for us to regard it as a collection of measurable sets. Similarly, the measure function cannot just be any function. It too will have requirements, but more on that later. Finally, if we package all three of these things together into a triple, so we form the triple of omega, s, and mu in the general case, then this triple is called a measure space. Tells you kind of everything that you need to know about what you're measuring and how you're measuring.